Hello, everybody. My name is Kevin Kotchak. I'm founder CEO of Chemical Q Device, here for discussion 109. And this is talking a lot about deep learning with quantum and classical parameters. So what I have drawn here is basically a PennyLane sketch. And the first two layers, the Hadamard gates and the RYs here, are non-trainable. So what that means is that the parameters are set, and over the course of many epochs, they just do not change. Now, on the right-hand side, this big block here is a collection of 60 trainable quantum parameters. The C0 gates do not train. It's the RY gates, and then I also put some RZs in here as well with some random values just to show. So at the end of machine learning, it's set with these specific set of parameters. Now on the right is a representation of ResNet 50, and that's more like in the millions of parameters. So typically in quantum, you don't need nearly as many. That's because of just simulation and the amount of information that's held in a simulated qubit. So basically, there's going to be two parts with this. So the first part is on deep learning parameters. And so I'll cover some illustrations, a good demo, and some real world examples with this. And then also part two is going to be the field has been accelerated. So as of Monday, there were 3 announcements with QML/QiML, in specific QiML. Quantum inspired, and I'll go over the differences between trying to get performance versus utility versus speed ups, and also some announcements as well. So for this first one here, so many of you that have done machine learning and deep learning, you're probably aware of this diagram. So basically in machine learning, it can basically have more reliance on the human, as opposed to deep learning with more layers to do feature extraction and classification. Now, in this specific diagram, the black lines are considered weights. It's not the actual nodes themselves, the dots, it's the connections that are assigned a specific value. And whatever is deemed by the convolutional neural network or the transformer to be more important will have a higher weight. Now, if the weights get too high, that can hinder training and require additional resources as well to keep passing that information on. Now, on the right, these are Qiskit diagrams, and then basically you'll see so that HRY for embedding the data. So basically, classical data has to go into quantum states, and then here I included a single trainable RY layer. So there's 4 quantum parameters here. And then so on the bottom one, more parameters. So if this has 1, 2, 3, 4, 5, 6, 7, 8, so 8 times 4 is 32 quantum parameters in this specific one. So this would have, basically more knobs. Now, the goal with everything in machine learning or deep learning is basically you want all those parameters set by the optimizer to be the best set of parameters that gives you the lowest loss, calculated by the loss function. And then that often corresponds to higher accuracy if those sets of parameters are correct like that. Now, this one on the left, I modified a little bit, and it's basically showing, so these are the connections, so these are nodes on the left. And, many people, you take it for granted deep learning, well, what about wide learning? Now, the reason why we don't have wide learning is because you take the number of nodes times the number of outputs as far as this computational demand, and it gets very high. So that's the reason why, say, for instance, in ResNet, 18 to a 34 to 50 to so on and so forth, is you're going deeper in that. You'll have a certain amount of width, but it's technically possible to have a single layer of this without going to second layer or second depth, second or third depth, that type of stuff. Now, it's the same thing with quantum. So we call this qubits, right? So these are analogies that are placed between these. And you can see it's a very similar model, but here it's with rotational values as opposed to the connections between here. And the same thing, like it's just well known that we want to go deeper, because, we're limited to, in machine learning, 30, something like that. You can go much higher for quantum machine learning in quantum, if it's not machine learning, it's just overall resources, what you have to deal. So that's basically limited in width by qubits times outputs. So that's the mathematical disadvantage of going wider in classical or quantum inspired machine learning. And you'll see here, so basically with the qubits, and this is called the measurement model, and everything gets converted. So this rich quantum information that's being portrayed in these 4 qubits, it all gets collapsed into a single, it's either a 1 or a 0 for every single qubit. So that's the measurement model. So, of course, we'd like to extract more information from this. It still works to some extent, and I and other colleagues have got similar performance, or maybe just a little bit better than the pure classical neural networks with these. Now, with this next one is basically, you have to know the difference between hyperparameters and parameters. So hyperparameters are the user adjustable knobs. So basically, your batch size, controlling how many images are fed in at a time. And then say, for instance, the learning rate of the optimizer, these types of things. Now they affect the end model parameters, but they themselves are not the parameters. They're basically used as a tool to make training work better, to get this end set of model parameters. And once you have that end set of model parameters frozen, you can do validation, you can do testing and inference. So that's the key, right? So between those two. Now, I really like this diagram on the right, and it's basically like, this is same thing for machine learning and quantum inspired machine learning, is basically you have some input, some data coming in, and you're going to have, say, an initial set of weights. So say like it's a pre-trained model, and you have like, ImageNet, these weights coming in. And over the course of time, you want your predictions to become more like the true values. Okay, so say your predictions are 90% of the true values. Well, that's reported as a loss function, and the optimizer will change the weights again to try to get this Y primer predictions the closest it can to the true targets. And this is this iterative process. And if you have or haven't done an extensive amount of machine learning, that we're talking epochs. Okay, so mini batches or epochs, but just imagine this is one epoch, and then it goes through. And then, it changes these weights again. And then it goes through, it's reported as loss function, goes back to Atom Optimizer or SGD or some other optimizer. And it's these weights right here that you're trying to get the absolute best in order to match the true targets, for known accuracy. Okay, so this next one, so this is basically dropout. So basically, I don't know how this came about, but basically it's been known to reduce overfitting, which means that the loss curve is getting better and better and better, meaning lower for training, and worse and worse and worse for test, meaning it keeps getting higher. Those two start to diverge. And to fix that, you can apply this dropout feature, which basically freezes the parameters on these specific nodes. So no longer does the neural network act like this, it acts like this bottom one, okay? And it's basically, the issue is these computers, get so good that they want to memorize the training set. And if you've seen these curves, you don't want to, do that. That's called overfitting. Like literally, it's just tracing point to point, like data point or image to image. And we want a generalized curve, y equals mx plus b. This is for quantum or classical, through it all. So when you introduce new data, it's not seeing this, overfit pattern. It's seeing some general curve that best applies to the model in order to get the best accuracy for your validation set. So that's dropout. And you can apply dropout in the beginning of the run. I think a lot of times you run for so often, and then you can say for these X's, those parameters will be frozen. Say this is close to 50%. So your dropout would be like 0.4 or something, or 0.5. And anyways, the other nodes that are hollow, those will continue to train it and try to get better. Okay, so that's dropout. Now there's another one called freezing layers. And basically in this all pink region here, is that this is a traditional neural network. So it's, as you can see, it's, as far as inputs are orange and then the screen is output. You see 1, 2, 3, 4, 5. So you see 5 layers. Okay. So in the bottom one, you see 2 of those layers are now frozen. So meaning if you choose to freeze them in the beginning or sometime in the middle of the run, those parameters don't get continuously updated. They're fixed. So, and again, that's used to reduce overfitting too. So figure like the computer wants to do the best job it can. That's what you programmed it to. But all of a sudden you can throw this in and, it's basically to get, like I said, at the end, better accuracy and lower loss of your validation set because it's not trying to over memorize the training set for that specific one. And this next one, so if you've ever done a bunch of these models, so I've actually optimized and improved a lot of these PennyLane models. And this is one of them that stands out because not only does it have a classical deep learning network, but it has the quantum circuits. Now, as it's set, it's a ResNet 18, which you can bump up to 34, 50. It's like one other thing you have to change, basically. So you can bump that up to a bigger neural network. That's just fine. But the issue has been getting both classical and quantum parameters trainable at the same time. And that's getting to that level too, which I haven't seen widely reported. It's likely going to take additional work too, because say PyTorch is, it has to treat the quantum parameters separate than the classical ones, basically. So what I see happening with this is basically this model type is like I said, as far as creativity and the number of things you can change between classical deep learning and the quantum circuit is quite interesting. And it also has with this ResNet 18 the pre-trained weights, these fixed weights from ImageNet coming in to help out things initially. Okay, so there's been a lot of great news, this week. Three big organizations posted, on Monday, GPUs with quantum physics, these types of things like PennyLane, and say for instance, Hugging Face, they have over 80 of these models. Why not make more ports for this that are more compatible? So typically with this one, I could use a GPU, but it was only for the classical neural network. And then, anyways, we want end-to-end differentiation between classical quantum parameters. We also want full compatibility with whatever simulator we want to use, Lightning.Qubit, Lightning.GPU, or other platforms too. And there's been a lot of these posted on GitHub, so they're definitely worth taking a look at. One person actually did it with text. So these are images, so ResNet's images. So they did a BERT model with text. And I think actually another colleague that comes on this discussion did that too. And, it's just from an innovative perspective. Oh, the other thing is you can use pretty much whatever data set you want with this. I got up to 44 classes, 4,400 images, and I'll show you coming up. But basically, this model is a good start. It came out in 2019. And then, in my opinion, it just needs greater compatibility, and then especially the trainable parameters between quantum and classical, and this is part in collaboration between NVIDIA and PyTorch, and then also within PennyLane. Just at certain steps, one would be like, okay, we have to fix these types of things, but figure like, as far as imagination, this one is like, this has been a standard for me to use. Now, as far as this use in industry, so I did this with basically 2 classes called ants and bees, and I bumped it up to 10 class brain tumor and 44 class brain tumor. And I basically couldn't change too many variables without running into issues with, like say, for instance, like with the 44 class and 44 images, I can basically just run the embedding. I can't run anything trainable. But the thing that was interesting here is it all came down to the data set. So the 10 class data set, as you see, the trend, it's trending to get better validation accuracy. This specific model, this quantum transfer learning model, to get the best performance, it's twice as many qubits as classes. So this is 4 qubits to 2 classes. And I kept it 4 qubits to 10 classes and 44. And that's why those accuracies are much lower. Because like I said, I was trying to do the analyze the number of parameters. So this lucky number 8 has been a good one for me, 8 or 9, as far as the number of layers, number of parameters, taking to get max accuracy. And that was the case with these. So this next one is basically all brain tumor images going from 2 to 4 to 44. And some of it's just, it just worked better with a smaller circuit, like just embedding. The higher you go up with not necessarily classes, but number of images is when things really start to bog down. And this is the quantum transfer learning converted from the Hymenoptera data set. And then in specific, you'll see the bigger one. Yeah, so you'll see these bigger data set classes. I only had it at max 40 gigs. Typically, it's a real, I didn't get much more performance. I can't bake much more in going from 16 gigs to 40 gigs with a V100 versus an A100. These are GPUs. So basically, these are all up on GitHub. And I've done efficiency studies, these types of things, and then also comparing it to other classical networks, Vision Transformer, and basically classical only versus classical plus quantum. So those are up on available on the repository there. And then, so this next one, this is brand new. So I'm just announcing this one today. So this is a kernel-based training of quantum models. Maria Schuld at PennyLane did this one. And it's very interesting because the variable I chose to change is in this strongly entangling layer that has some types of 2-qubit gates and some types of trainable single rotational gates. So the first one was 8 layers for the strongly entangling angle embedding to begin with C0, and then lowest loss is 0.046. This next one, the best one out of 10 layers, this is 30 experiments across, these 3 sets of experiments. And then in specific with this one, I got the lowest loss to be 0.059. And it was, the runs themselves are predictable, run to run. But this one in specific with the CZ was, as you can see, kind of up and down. The first 2 were, lower at the end, but it was just a lot more fluctuations. And the CY, as you can see, I would say that this is the most consistent and across different layers. So again, it's angle embedding plus a single layer of strongly embedding, or angle embedding plus 2 or plus 3, like that. And so basically what this all boiled down to is I increased the speed by switching from lightning.qubit to lightning.gpu. It helped a little bit. And then improve the runtime significantly from parameter shift, which is meant for hardware, to adjoint differentiation. And this was, Maria mentioned this in the demo. And then ran the experiments. And then this is what I got. So all experiments with at least 4 ansatz layers, so meaning like a layer of rotational gates, and then the sequence of 2 qubit gates, had at least 100% test accuracy if there was 4 layers. The CY circuit with the 8 layers achieved the best loss minimum. Runtimes for 10 layers favored C0 at 95.8 seconds. And I was expecting CZ to be the longest, because a C0 is basically a bit flip and a CY is a phase flip. And then CZ is both a phase flip and a bit flip. But anyways, it looks like the computational demand with the CY and the CZ were about the same, And there was also a separate embedding quantum circuit. It also achieved perfect test accuracy. So it's worth trying to bump up on data set size, because it's hard to tell if everything's like the iris set. This is like 50 images here, 50 images, this other flower set here too. Okay, so research and development with parameters, and it just needs additional research. I think this is coming too, because like I said, I picked out probably about, these 8 big articles that came out within the last year. And then all of a sudden we get 3 in the same day. And this is on Monday. And I'll get to those too. So first use case is quantum parameters are more effective than classical parameters. The machine learning optimizer needs to more efficiently adjust individual rotations for qubits. It could do it on its own, but like I said, the tricky part is having the model that's the closest model is this quantum transfer learning model, it appears, is to do all, everything well, right? And we're talking classical data generation, it's very similar to what regular machine learning is. So all this should be possible. And basically,
hi, Kevin.
Yeah, go ahead.
Can I jump in and ask a question?
Yeah, go ahead.
So in the previous slide, you were like mentioning about C0 trainable and CZ and CY. So does it has anything to do with the expressivity of quantum circuits?
Yeah, I think this is what we're talking about. So say, for instance, like there's been a lot of papers on expressivity. I think the trend is to go to inductive bias and more specifically contextuality is what they're saying is as far as having a specific quantum circuit for a specific data set. But yeah, typically with these types of things, with lower losses and higher accuracies, you're typically talking about expressivity, these types of things.
Okay, because like I'm working on quantum machine learning, and for my model, like single qubit was working better than multi-qubit systems. So I'm wondering like how I can address that issue. So that's why I was asking like,
yeah, there's a good paper.
Here.
There's you probably know the Seth Lloyd quantum embeddings paper with Maria Scholl and a couple, I think it's a Ruza Chizes with a couple other researchers. And they were able to basically take a binary data set and then map both of those, pure states on opposite sides of the qubit. And then the next step up was actually the quantum transfer was actually the Hymenoptera data set. And it looked like they had good success with that too. But ultimately, you're trying to get the data sets just basically one image after another for that class on one part of the exterior of the qubit, and then on the other part of it, the exterior of the qubit. And if you figured it all out, this could potentially be a more effective way of separating data sets, right? And we're not talking about speeds, we're talking about just quantum physics helping, with classification.
Okay.
But yeah,
can you repeat
really
the title
specific.
of that paper again? It's quantum embedding.
Yeah, if you go to scholar.google, that one that should be the first one, just quantum embeddings, and then Lloyd Lloyd.
Okay, I will search that.
Yeah. Okay. And Maria, who actually wrote this model, is also on that paper too. And it gives you a lot to think about. You might have to read it a couple times.
All right. Okay. Yeah. Okay. Thank you so much.
Yeah, you're welcome. So the second use case is basically quantum parameters supplement classical parameters, which means everything's working well together. And using this quantum transfer learning as a model as a template, and it's been referenced even by Maria Scholl. So this is Andrea Maria I'm talking about. She gave a talk within the past month, and she referenced quantum transfer learning as far as trying to find examples of data sets to compare, to present on at a conference. And this is one of the big models. So yes, I mean, 2019, it would need additional adjustments. And actually some on, with PyTorch on that end too, with the optimizer, it seems to be the issue, with classical plus quantum parameters. So obviously doing the classical deep learning parameters at the same time, and then quantum circuit also. And, it's not meant to really place blame on anybody, because, I mean, the tools that we have are so cool because like we're working with machine learning in a completely different way. And I think it's pretty clear, that I guess the priority should be placed on these advanced, hybrid models with, awesome classical deep learning, maybe for Hugging Face, the PyTorch background, and then PennyLane circuits, these types of things that just mesh well together. And I guess the third one is basically further experimentation. This is more like trying to understand the physics of the data sets in specific. Okay, so these are helpful. So I asked basically as ChatGPT, is there a metric for number of parameters for model complexity? And it gave me all of these as far as removing parameters. So you'll hear a lot, we've progressed so far. ChatGPT has trillions, 11 trillion parameters, and these are all fine. But a lot of times, if the data set or the problem doesn't necessarily need that many parameters and it's essentially not using them correctly, then it makes sense to, like this first one says, to prune the unnecessary connections that don't make sense. And then also there's certain neural networks that are more efficient than others. Now, I haven't done a full out study on say the past 5 years of neural nets, but some of these are older. Say, for instance, MobileNet, EfficientNet, SqueezeNet. So, you may have some inefficiencies with larger models, that just might come with the territory. And regularization L1 and L2, I've touched on this. So this is basically like weight decay. So this, you don't want huge weights, so that's computationally expensive. So this would be if you're going up to 1 and everything's like 0.9 to or 0.7 to 0.9, like all the different nodes or qubits, then that can be brought down. And then limit the depth, especially the width. And I talked about the nodes times outputs or qubits times outputs. That's what's computationally demanding. And then knowledge distillation is taking transferring knowledge from a complex model into simpler. So if there's just a brand new transformer model that comes out on the market, but you don't need nearly that size, but you want to distill from it, this is what that's talking about, I believe. Quantization in this specific case, and this might help quantum rotational angles, reduce the precision of weights and activations to reduce costs. This is basically saying, like, if we want to know every time the quantum algorithm updates, we want to know that it's like 0.11156 or just 0.11 is fine, So I don't know if that's been taken care of, but that could be one of the things that would increase efficiency with quantum parameters and classical too. And then also multiple simpler models instead of one big one can work. I think that usually you try to use a single one, but in certain cases you can break it into pieces. And then I've touched on this, is basically transfer learning is taking all of these weights from like thousands of classes and millions of images, and those weights are what you're starting with before you actually start training your neural network. So this is common. It's either called transfer learning or there's a button or there's a line of code that says pre-trained equals true or pre-trained equals false. And usually you set it to true. Hybrid machine learning plus deep learning methods to reduce parameters. So say, for instance, like a smaller support vector machine with, deep learning attached to it. And then, so this is the next part. So I'm calling this the acceleration of the field as of Monday this week. And I'll get to some of the performance utility speedups and announcements. So all of these came out on the 13th, Monday of this week. Terra Quantum announces hybrid quantum computing collaboration with NVIDIA. And a lot of these companies have been implicated with quantum hardware, but we are using our hybrid quantum algorithms delivered on NVIDIA GPUs to deliver significant business impact today. So we're talking about practical applications. A lot of times it's machine learning, deep learning with quantum. And, say, for instance, say a whole new range of opportunities that they can do. Now, the classic, this is, all of these are NVIDIA. So NVIDIA is their cuQuantum in specific is their software that meshes with PennyLane and also with Qiskit and then TensorFlow Quantum too. And so say, for instance, on this one, in collaboration with NVIDIA, Classic will establish a multifaceted research landscape. This is a hospital system in Israel. So Classic is based in Israel, and Classic has a number of partnerships that they've formed at this point. If you're unsure about the technology in these headlines, look for GPU and then That's the easiest way to find out how exactly they're trying to utilize the technology. And they're using H100s, which today, and I'll get to this a little bit later, as of today, the H100s are the top, NVIDIA GPU that people are using for many applications. And so this next part here is basically BASF. So BASF has kind of been in the news before with quantum, but basically they're saying, you want to look for these words too. Like if you're using quantum mechanics, quantum physics, PennyLane, Qiskit, if they use the words traditional, like they say versus traditional or better than conventional, these are kind of the buzzwords that, you're using some type of quantum inspired machine learning. So it says the BASF researchers are demonstrating how a quantum algorithm can see what no traditional simulation can. Okay. And they said they got up to 60 qubits. And like I said, I don't think that's with machine learning. And I guess the way that people think with quantum circuits is I would assume just going a lot deeper and having a lot more quantum parameters because of the limitations of simulation. And then it's the same issue with qubits times outputs as nodes times outputs too. So those were the big three. And then this is basically the past year. So you see these big names, and NVIDIA themselves have done, thousands of GPUs with this, with quantum state vectors, QCware, for big step change in performance. And this one gets advertised a lot to me, this PennyLane, NVIDIA, NERC, and Brookhaven, accelerating massive simulation of quantum systems. So, to me, it's, it takes a while to sink in, but like basically GPUs are the thing. And here it says with Wall Street Journal, GPUs transformed AI, now GPUs for quantum, quantum equations, quantum software, GPUs. So, okay, and then Sandbox is everywhere with quantum. So cybersecurity is a pressing thing right now. They've also got this biotech kind of life science partnerships with UCSF, for cancer, Alzheimer's, Parkinson's, and they'll say physics-based. So if you see something like physics-based machine learning, that's probably, this quantum-inspired, and especially it says massively parallel classical hardware. The ACM paper is basically saying to get anything close to an A100, pretty good GPU these days, you're talking about decades. And you might not even be talking about machine learning workflows. You might be talking about something that supplements quantum inspired. And then BART has had these two, is basically, they say it has great potential, and then also for simulating embedded systems as well. Okay, so this is, so we're not talking about speedups here. We're talking about just the differences of quantum mechanics. Now, quantum physics is up here, and quantum mechanics is the specifics of basically quantum computing. And we have these superpositioning, entanglement, and quantum interference effects on hand. And with quantum inspired, you have pure quantum states. So meaning that these calculations that you're doing are on the outside of the block sphere. They're not on the inside, and it's by Ket notation instead of by density matrix for that. And then there's no, basically there's no need for shots in a lot of these models. It's just like, it's not restricted to the hardware. It's running the algorithm and it just gets the answer right away. And that's pretty much exactly how machine learning does things anyway. And even though, so processing is done classically, so you could even alter the physics, if it's finding to be, increase, the efficacy and keeping it in safety, say in medical at that same time. Is there an even better way, than the way that we're simulating physics today? And then also, we talked about this a little bit, maximally separating data classes, especially with QiML, so we can be on the outside of the block sphere, have different data sets at different points too. So, and this quantometric learning was hot for a while, and they had issues with overfitting. They had a demo out on PennyLane, and I think they took it down. just because you could get great accuracies with it, but if you don't know what you're doing to say, install dropout or freezing layers in quantum, then that one, can get out of hand. So the quantometric learning did a lot of, this fundamental research. This is the Seth Lloyd paper I was talking about with quantum embeddings. A lot of this good fundamental research as far as just how could accuracies get better? How could you get new utilities without even talking about speedups in these cases? Now, a lot of this information that I get is based on these Cicero researchers. It's a quantum-inspired machine learning survey paper, and it's quite long. And they say, as QiML continues to evolve, we anticipate a wealth of future developments drawing from quantum mechanics, quantum computing, and classical machine learning, enriching the field further. So this was September of this year. So that'll be, I should have the references up later today or tomorrow. And then, so for this next one is speedups. Okay, so QiML algorithms that we can't dequantize today, meaning that the quantum mechanical effects of these algorithms are still intact. Basically, it's like there's no way to replicate that classically. So there is some uncertainty with it, is like, will it ever be the case that, we'll find out methods to take every QiML algorithm and dequantize it into classical? That's still to be seen. However, few quantum algorithms have been dequantized into regular algorithms so far. So it's in this QiML paper, basically, and it's, backed up by all these other papers as well. Now, if it's the case that we're going to use QiML or, QML in the future, probably the further future, it could be used as a tool for dequantizing algorithms into conventional algorithms, meaning that you wouldn't need extra RAM, or you wouldn't need, QML library software, these types of things. Okay, so that's still to be seen. And I keep rereading this paper, and it's it kind of shines lights on this in different aspects. But basically, it's removed of quantum mechanics information. You start, with algorithms on, quantum simulators, these types of things. And then there's a specific rubric you have to follow. And it basically, if the classical algorithm has very similar performance as the quantum one does, the classical one will be preferred because it doesn't take a simulator, it doesn't take extra RAM, that type of stuff. So some have been dequantized. So I think it's just something probably down the line a while. And these are the two main use cases, just full out QiML research, and then also dequantizing some algorithms that we're going to see. So both of these refer to time complexities. So this is not referring to, say, for instance, superpositioning, entanglement, and quantum interference in the sense of mapping data sets better, right? So, there's different roads that this could go, and it'll be interesting to see, based on all of these, recent organizations getting involved, what will happen. And the end goal of this is we're trying to keep as much of this quantum mechanical information as possible. Now, some of the architectures, especially the measurement base, is basically, you have your incoming data set, it gets converted into quantum states, and then so that's the embedding, and then you have the variational layer, and that could get trained, to optimize those parameters. But when it gets measured, everything goes back to 0 or 1, right? So that's where you're losing some things along the way. So, and the optimizer likely accounts for that, but it's still needed that we need to keep more of this information and lean on quantum physics even more than we're using today. Okay, so here's what's coming up. So basically, immediate impact by key organizations as a working technology. So that's in the earlier slides. And then quantum mechanics number 2, quantum mechanics and large data set interactions need to be better understood. So this is the core QiML workflows, dequantized algorithms, or even modifying quantum physics. These are things that I think IBM, so Qiskit Dynamics can do things like that. Now, in the 3, it's basically potentially replacing ML workflows for QiML workflows in key industries, maybe more on the performance utility side as opposed to the speed ups, because you'll lose some of the speed throughout the simulation process, even if it is a quantum speed up algorithm. And then lastly here, so this is actually there's one more slide after this, and then this is back to the Cicero researchers. QiML represents a multifaceted research domain with investigations pushing to exceed conventional, classical state-of-the-art results or exploring the expressivity provided by quantum formulations. So we've talked about conventional, so conventional is like how we see machine learning today, running on multi-node clusters. Expressivity is definitely, and MIT's done a bunch of those studies with expressivity, and there's not always do you want the most expressive gate in that single location. Okay, so this is basically parameter advancement's near-term outlook with this is a lot of these tools are currently available. So we have lightning.gpu. There's also lightning.cocos, which I haven't got to experiment with as much. And then this is basically on, you could use GPUs on separate nodes. Now, a lot of this just carries over from classical. So MPI and these COM, I think batch ops is unique to quantum, but adjoint differentiation is for quantum too. It's basically like back propagation, but with a quantum circuit. And like I mentioned earlier before, the ACM study with A100 versus a future QPU based on bandwidth is likely decades out. So the second one is the second quarter of next year, we're supposed to be getting new GPUs. So if you don't know, so an H100 is up here, and then an A100 is a little bit below, and then you have a V100, and then some other ones below that. And they're saying faster and larger at 4.8 terabytes a second, and then also, RAM bump, 141 gig capacity versus 80 gigs. And the A100 that I can run on it is actually only 40 gigs on Colab, but it can go up to 80. But anyways, the new standard looks like the 141, and there will probably be an A200. I'm not for sure about that. The H200 is like the super industrial one. And anyways, this will all equate to more parameters, 1.4 times more bandwidth than the current H100. And then I included at the bottom here, you see parameter growth. So this is 1954. And then in more recent years, you see the spike up. And these are likely the large language models, NLP, these types of things. So are there any questions about the specific slides? I saw Jacob, so you put L1 and L2 for quantum models, how? So a lot of these just directly, so my assumption with it is basically it would limit the rotation angles on it if that's what's causing it to, consume the most resources for that specific one.
Okay, I imagine that in quantum-inspired models, that would be trivial, but you wouldn't be able to go back to pure quantum models. But yes, so that the issue is regularization would be difficult unless you simulate it with a lot of additional qubits.
It depends on a number of factors.
Mm-hmm.
I think the big trend will not to be go high on qubits. It's just basically find ways to make use of more and more parameters going wider, or I'm sorry, deeper into it. So
yeah, I imagine that it applies to all nonlinear transformations, which would be difficult, where classical models would clearly step in, but the difficulty would be maybe you could combine classical and quantum models in a hybrid structure to achieve some of the regularization in traditional neural networks.
Yeah, I think the big thing, because like I said, I'm on the discussion forum for PennyLane a lot, or technically Xanadu. And I'd asked previously about the quantum transfer learning, and we set the weights to be on for the quantum circuit and the deep neural net, or the ResNet 18. and it changed the values, and it ran slower, which likely meant that it was doing something. But I ran it on 2 data sets, and one of their researchers ran it on one of theirs, and I didn't see the gains immediately there. So there's other issues. I mean, GPUs will be the performs, or will be the, what everybody wants to run on. And some of the models, say for instance, like if it's like I think it's if it's PyTorch, NVIDIA, there can be issues with kicking on. Basically, it appears that the RAM gets shared between the classical processes and the quantum processes. So say you have 40 gigs of an A100, and all of that has to be synced up better, right? It's basically still all classical. It's taking advantage of quantum physics, but there's some parts missing that it's not like full compatibility that you have to use like jacks for. Or if it's just like, if you want to only run a quantum circuit model, and I benchmarked on one of these models and just going up and up and up, say CPU, TPU, V100, A100 kind of thing, that one ran well, right? But I think there's still, on the classical machine learning side, more so with PyTorch, maybe less so with TensorFlow at this point, that these need to get synced up better, so the results ultimately get better. But if I were to say the 2019, the quantum transfer learning model was ahead of its time. However, I haven't seen anything get iterated on this specific type, although there's been lots of other different models that are completely, touching on different aspects of machine learning. So I just think it's the best bet is like have a classical deep learning neural network. Now you have a quantum circuit, and then just try to make the quantum circuit get even better performance. That's a good use case.
Can I ask another question?
Yeah.
Recently, I tried to run one of the standard GAN models from the PennyLane tutorials on pure CPU, PyTorch on a GPU, but a quantum model on CPU, and then everything on GPU. And the CPU was still giving the best result. Is this because of you need to actually need to tailor the whole solution to run on GPU? You can't simply use the standard CPU designed model and run it on GPU, or it's something more problematic with the way PennyLane works with GPUs?
Yeah, well, there's two things going on, because you have the simulator like you're choosing. So it's like a default qubit, lightning qubit. Those are both CPU based. And then, you jump up to the lightning.gpu. Now, also, I don't know if you use Colab or if you have a local GPU on your own system, is that, yeah, it is local.
Yep.
Yeah. So that's a different thing too, because I can run a single GPU if I put a specific, like it's a PennyLane CUDA code in, and it takes care of all the PennyLane stuff and the CUDA stuff. And for specific models, it runs well. But I don't believe I've had it where I actually get different accuracies. It's more like it'll either get hung up on one. Usually
it's rather than accuracy is the time. So it's I think it must be a lot of swapping between GPU and CPU in the way they handle circuits and shots.
Yeah, I mean, I could see, like, say for instance, like a V100 or A100 that I'm using on the quantum transfer learning model with default.qubit, which in itself is not taking advantage of a GPU for the quantum circuit. My V100 or A100 gets hung up on the first qubit. It's like that, with that specific model, there's something not optimal, so that's an issue. But the good thing about their discussion forum, this is Xanadu or PennyLane, is all of their top researchers are on it. And a lot of times if you call out somebody, who wrote the model, you won't get them. But just say, hello, I'm having issues with whatever. And then maybe eventually it'll get to the right spot. I just get the sense that there's a lot closer connections between these demos on Xanadu than some of the other platforms, as far as like people are actually readily using this. And if you search for QML dot, C not or QML.ry, it's PennyLane that shows up in the Google search, So yeah, I mean, you just have to, you got to keep moving, right? So just keep moving through models and, they'll be aware of these things, and there's bug fixes. So I saw one today. They said, oh, this is a bug. We'll put it in for whatever. And I think ultimately they want everything to get better, and so do you, but it does help to kind of, voice whatever's not working.
I'm sure it's the early days of GPU based quantum inspired models. So,
yeah. Did anybody else have any other questions?
Yeah, Kevin, I'd like to know, so like, where is the actual hardware you're running on?
Yeah, so it's all, so say for instance, like a lot of the simulators are free, like the non-GPU based. So anything from like Qiskit.air, I think it's in Qiskit's possession. And then so like a default.qubit or lightning.qubit. These are, a lightning.qubit is like a more advanced CPU. I think that's, that's going to be PennyLane's. Google has QSIM simulator, and they also have.
So all of the stuff you did was on simulators, not on real
Yeah, the
qubits.
part where I'm not 100% is because like I can run on Colab and it's using the RAM from just if I ran classically, but I could put a specific line of code, and then it also is appearing to help the classical aspects of the notebook and the quantum circuit. It definitely helped the quantum circuit because that was the most like costly part of the model. So yeah, it's mostly, I don't know exactly the physical locations where they reside.
Yeah, because what I was interested in was how you got the GPU and the quantum computer to be close enough to be able to run the same in the same model building. And then, if you were able to actually do that and not just use simulators, I would be really interested in seeing how you set up PyTorch to do that. But
Yeah, a lot of it's built into the demos. It's just like if you were to like do a transfer learning model with pre-trained weights, well, you're capturing that previous work that was done so long before. Now, I bring this up because like PennyLane has at this point like 27 different QML models, and depending on the model, it's already baked in with PyTorch, or you could just do really heavy optimizations with batch size or whatever you want to do. But a lot of it's just, you could do things from scratch, but I wouldn't waste a year on it. And some of these that I see are very complex, like with Covalent, which is like this scheduling service that, classically that you would use. And if anybody said they knew all 26 or 27 of the PennyLane demos, I'd say you did a pretty good job, because I went through and optimized the parts that I can, but there's still aspects that you would have to, research these models more and basically change them in ways, modify them in ways to get to your own objectives too. And you just cite your sources when you're doing this. Yeah, so I'll have the references up. It should be later today or tomorrow. And then I saw some regulars hop on as well. So Anand or Ron, you can go ahead.
Hey, Kevin, how you doing?
Pretty good.
Good. Yeah, so when you're out there running on in those services like PennyLane or something, and you're pulling up what you think is a QPU, you actually might be running on their simulator. So you're not and I'm not sure what access PennyLane or Xanadu has to real hardware. But the cool thing about them is their framework for quantum stuff has that Python decorator, which you wrap around the quantum stuff. And the quantum, then at that point, the quantum stuff can be shipped out, has to be wrapped up, sent to a queue for a real quantum run, and you have to wait for the quantum run to happen, the results to be collected, and then returned to you. So your whole environment kind of comes to a standstill when that happens. But if you have that wrapped up with one of those decorators, and you're running a simulator, it kind of does the same thing. It ships it out to the simulator, but the simulator might actually be right in your rack because, like you're saying, it's an NVIDIA. It might be an NVIDIA based thing. So,
Yeah.
and you probably don't have to wait. You don't have any queue times or minimal queue times. So stuff goes out there, but you still have to send it out and wait for it to come back before you proceed with your classical part.
Yeah, I mean, all of the QiML stuff, the only thing I've gotten delay on is I was trying to do A100, I think yesterday, and then it was just taking a little bit longer to kind of kick in. So say, for instance, when I switch between, a V100 or A100 or a CPU, it disconnects and deletes the runtime. So then you have to do some of your installs again. So say if you're on Colab, pip install PennyLane. And if I have a drive, like my Google Drive going, I have to reconnect a drive between switching to devices. But I think the biggest thing is that I was watching some of their applied mathematics. I think it's in Los Angeles, and they had the top QML researchers, on it. And Maria from Xanadu was talking, and she said that, all this research that they should be doing in hardware, and then switched over to results. Somebody asked her a question, is this on a simulator or on real hardware? She's like, or they just asked, is that real hardware? She says, oh no. Because there's many things like decoherence, there's noise, there's you have to do many shots, with hardware that I don't think there technically is a QML workflow yet and it likely won't be for some time for anything hardware related. So yes, yeah, they're not readily available. They're too expensive. Everybody, there's the use cases there for workflows. For big problems on small data, in the coming years, likely, but not for workflows, which is what most people want to do. They want to train and make your parameters the best they can. So then when you put in your new data, then it's due to all that hard work and machine time that it took to get to that point, right? So many iterations.
Yeah, and I think the workflow is basically the same. Is you just got to be willing to wait for the queues to run your job and deal with the fact that the quantum stuff is still not fast, and the results have to be collected and returned to you. If you have that quantum step as part of your machine learning iteration, then every cycle you go through it, you're going to have a call to a quantum computer. You're not going to like that if you got to wait an hour to get a result from a real machine. So that's,
Yeah,
people are giving
there's
up
so
on
many
that.
steps
Yeah.
away. Yeah.
Yeah. But the workflow is there. It's just that, until the quantum computers are bigger and there's so many of them that people don't have to wait for them. I think people don't want to wait the time, because in the meantime, like if you're on Colab and you're paying for an instance, that instance has to sit there and wait for it, and you have to pay for that entire machine to sit there and be idle waiting for the quantum results.
Yeah.
So
Well,
the workflow's there. It's just a matter. It's just not practical.
Well, all of the deep learning that I've seen in actual use, the model building is all done in batch. I was at a huge enterprise, and they had a couple of Cray supercomputers, and these supercomputers are just filled with GPUs, and the data scientists would do all their work during the day, but then submit these to be to run overnight to actually build the deep learning model. And then once it's built, then you can just use it, and you don't need all the fancy hardware.
Yeah, and in those cases, if it was all classical, it runs the whole thing beginning to end. There's no pauses in the looping to go out and wait for quantum hardware. Everything can be done on the classical computation. So basically, once you get in line for all that high performance resource, your stuff runs. It runs probably pretty fast because, like you said, it's a supercomputer.
Yeah, well, yeah. What I'm getting at though is that you're already waiting overnight. They're training your models at night in batch. So if overnight it has to wait an hour extra to get a quantum computer, that's no big deal. It's still going to be there for you in the morning.
Yeah, but it could actually be worse than that, because every time you jump out to run a quantum job on real hardware, you were dealing with waiting for a queue, and some of these are notorious for being in the hours. General, typical wait for some things like on IBM is like an hour to rest of the day. So it's, and all these sites have got big demands on their actual hardware. So it's not, it may not even be an overnight thing. It's, you gotta, at every point in your ML iteration, if you're going out doing a piece of it with quantum, you gotta wait, you gotta submit it and wait for it.
Yeah, well, I guess what I'm getting at is, the people doing this, it's a different mindset. I mean,
Sure.
we're all used to having desktops and laptops where everything is immediate. You do a Google search or a Chat GPT search and you get something back immediate. But when they're training these models, they're used to waiting significant lengths of time to do it. So if it's 24 hours, I think they would just take that into consideration when they're working.
Yeah, I
Yeah,
think you go ahead.
I guess that'd be true if the job is big enough and they have plenty of money.
Yeah, I think a lot of it goes back to there's a Chris Worley and Chris Ferry book out, and it's Quantum Computing for Babies, and they go through the difference between having 2 bits and superpositioning with a qubit, and they say this is for a really big problem. That's what a QPU or quantum hardware, but not like a workflow, like a dependable workflow. You need to, like, something didn't work, I need to run it again unless you own it. And even then, many years out for error correction, those types of things. I wanted to see if anybody else had any other questions or comments. So Raul or Cynthia? And then if not, Edwidge or Rufino? And then I still see more people that have come on before. So Anand or Mike? And like I said, I should have this deck up probably later tonight or tomorrow. And yeah, it's definitely it's definitely like it's a working field. I think that's the main difference, because like the news from Monday is like this technology works, and there'll be accessing GPUs and it's nothing compared to some of the other emerging technology, right? Working into machine learning workflows. I would encourage the rest of the industry to put some of your notebooks up, because it'll help the field. And I do see some of these other ones that even this past year that have committed to GPUs with quantum, is that I think I'm seeing them on the Xanadu discussion forum, multi-node GPUs, that type of stuff as well. But it helps everybody because as far as like a fully medical product and these types of things, like it has to go through many more ringers, right? Like, so when I put my stuff up, I know that whatever I put up, I'm going to have to develop even more, if it's make it faster, higher performance, these types of things. And I think the industry shouldn't, be afraid to put up some of these, their multi-node, multi-GPU notebooks on machine learning, just because it'll help speed up other things too. But, for working technology, and we have quantum physics, principles to take advantage of. It deserves the type of, I guess like the full-time work that like a deep learning scientist is doing right now, right? And there's a lot of those. There's a lot of classical deep learning scientists, and they're actually closer to QML or QiML than many people that do just quantum algorithms, right? Because it's more about machine learning workflows and less about the quantum circuit. So, it's just it's hard to put a point on it when an industry breaks, but it's definitely, like I said, like a ton of stuff the last year, and all of a sudden this this Monday, 3 new things, and they're just like, they're big companies. Well, Terra Quantum's big in quantum, but they're still a startup. But it doesn't make sense not to put your notebooks up, share this technology. Don't be afraid to ask questions on the forums. I wish there was more going on in Qiskit with it. I asked if they could do like weekly discussions this week on QML/QiML. I don't, it's the technology that makes sense, and it's the practical one. And that's typically how things work. It's not the one that's like the shiny bells. It's the one that's like actually works, and we'll have some advantage, and we'll have a lot of advantage for many years. So anybody else that we haven't heard from? You can go ahead.
Just have one comment, Jacob.
Go ahead.
Yeah, so you mentioned that we could get on GPUs 60 qubits processing, which is quite impressive. But to actually use lots of qubits on real quantum machines, it's a lot of gymnastics. So if you look at the 127 qubit machine, which you can access on IBM Cloud, to actually do, let's say, a quantum neural network on it, it will not work unless you do a lot of preparation and a lot of thinking how to handle errors. So it's not easy to transfer from GPU computing to the real machine. It's not instant. It will require a lot of rethinking of how we actually handle those big machines and lots of qubits. So just a comment, we can't simply say, let's get more qubits. It's not going to work unless we start thinking how we program them in different ways than we program classical machines.
Yeah, and maybe the low-hanging fruit with that is to figure out what the widest layer has been for nodes. So it's basically the same issue, because it's nodes times outputs, and then in QiML it's qubits times outputs. So that's the main thing, right? Because when you have something times something, then it's like, well, 2 times 2 is 4, but 2 times 3 is 6, and 2 times 4 is 8. Well, but it just, it does not. It's technically possible to have a single layer, right? Classically, and I think you actually might get your best results. But the reason why it's deep layers is because it's the nodes times outputs, where they have to go like ResNet 18 and then ResNet 50 more layers, not wider. So I don't see that. If you have specific tasks that you're looking to solve, you can share, but I see it more being used for just total number of parameters going deeper, just like deep neural nets. Like, yes, having some width to it, like 4 or whatever initially, but just how can we take advantage of that many more quantum parameters than if we were much shallower.
Yeah, but I think decoherence is going to kill us is going to kill us in other way. So either depth or interactions between qubits. So the error mitigation on real quantum machines is still priority number 1, and we're not going to get high fidelity operations very soon. But we can get them on GPU systems.
Yeah, I would stick to the GPUs, you know, for the next several years for sure.
Yeah.
Anybody else we haven't heard from?
So a comment on the 127 qubit IBM Eagle. If all your experiences with that is you're facing an uphill battle because IBM's double hex topology is just has problems, and so you can't just make a circuit wider and expect better performance, because it turns your algorithm into a whole mess of swap gates, because the qubit connectivity is only, some qubits are only connected to 2 others, some are only connected to 3 others. So to get information from one side of the chip to the other, they have to insert all these CNOT swap gates, and everybody knows CNOT gates are noisy as hell. So IBM isn't probably not a good platform to test that on. As the neutral atom machines come online, I think you probably see better performance.
Awesome. Anybody else? Appreciate everybody coming on. So yeah, follow this on LinkedIn. Again, I'll have the codes up on one of these is a brand new study, the kernel study, that'll be up on GitHub. And yeah, I would definitely, if you haven't started coding with it, just go to PennyLane, and then just go to quantum machine learning demos. That's a good start. And you can go to Qiskit. They have about 12 of them as well. If you were doing TensorFlow, it might be a good transition for you to do TensorFlow Quantum, just because the GitHub seems pretty active, and it's I guess I'm not seeing like direct paths for what I need, but it's still something. It's Google basically, but TensorFlow Quantum, and you use Circ, I think, for circuits, and you can use Keras or TensorFlow for other optimizers too. Awesome. I appreciate everybody coming on. And any other last questions, Fakhar? Anybody else?
Yes. So you were mentioning about TensorFlow Quantum. So I was trying to run some circuits from TensorFlow Quantum, but I think so it's not being compatible with the current versions of Python.
Right.
You might
Yeah,
have to degrade towards 3.7 or something, but I was having a hard time to run those circuits.
Yeah, I too. Like, it's supposed to be 3.9, I believe, but the weird thing is it seems like other people, and I don't know if you know Owen Lockwood. He does a bunch of the tutorials. He's done like at least like 30 of TensorFlow Quantum. And anyways, it's been working for him. I had gotten it to work several months ago. And anyways, Google was one of the earlier to the first quantum supremacy for hardware 2019. And anyways, in any industry, you want to have two, right? You can't just have PennyLane, you can't just have Qiskit, you can't just have TensorFlow Quantum, but I mean like a good two, moving forward, like that's the industry's preference. That's nothing to do with the developers, right? So yeah, I mean, the others have to get better. Qiskit said they'd put, more demos up, but it'd be a while, is what they told me. But yeah, you won't get by with just one really good QML platform, right? So hopefully the news will spark things. And you can also, Fakhar, go on their, they have GitHub, and you can ask questions, and it's still pinned on mine. Can you please help me get these demos to work, was my question. And that was the answer.
They do also have like a Slack channel for TensorFlow Quantum as well. Like Qiskit has their Slack channel.
I haven't seen that one. You're saying they do?
I'm just asking. I don't know.
I haven't seen one. I'm on Qiskit Slack a lot, and I'm on Xanadu Slack a little bit, and then Xanadu discussion a lot. So, but yeah, I think it helps the industry move forward. I mean, eventually, I don't see everybody sticking around, but it's the same thing with like the closest analogy is PyTorch and TensorFlow, right? You can't just have one, right? So if you want a QML platform, there needs to be a good solid two at this point. Everybody's
Yes, yeah.
yeah, and everybody's feel free to go on GitHubs and Slacks and these types of things and just ask questions if you can't get their demos to work. The thing with PennyLanes is their default is it usually 99% works on Colab. Just install PennyLane and it just works. The Qiskit ones, I got 11 out of 12. I had a compatibility issue that it was working in March, and then anyways, it isn't working now, at least part of the demo. But it's really the developers that drive it all, and people really wanting to do this. You see the news, you got to make up in your mind, like, I see the financials. QML is supposed to be worth $5 billion by the end of this industry, and you'll have to commit to it, right? And I think the probable benefit is a lot greater than the risk at this point, especially with everybody kind of hopping on the GPU quantum bandwagon. So yeah, but keep at it, Fakar. And I don't know if there was like if you previously work in TensorFlow, that type of stuff, but it seems like there's activity. I got the demos to run, and like you said, Python version issue. So
Yeah, because like I got some papers and they did their simulations on TensorFlow Quantum, and I was trying to run those codes, but it was not working. And then I went back to their GitHubs and they mentioned the Python version and everything. So, but right now, like 3.7 is also degraded, like Python 3.7 also. So I'm still having a hard time. I couldn't run that TensorFlow Quantum systems.
And that circ.qsim is like a 90 core Xeon processor, and it's not the same one as they called it QSIM back, for Quantum Advantage in 2019. Anyways, I think it's on par with the lightning.qubit, which is PennyLane. And I did a PennyLane model. They ran about the same. The Penny one a little faster, I think, mostly because is native to it. But anyways, they seem to support QiML, with simulators and that type of stuff. But just keep at it.
Yeah, I mean, Qiskit and PennyLane, these two models work very well. Like most of my work is based on Qiskit and PennyLane. So I have not done anything on TensorFlow yet, but just from the other papers, just to trying to reproduce their results, and it was not working.
Yeah. And I could talk all day about this stuff. Anybody else? Last questions or comments?
Well, thank you so much for the presentation, Kevin.
Yeah, appreciate it.
Yeah, thank you, Kevin.
Yeah, thank you. So we'll see for next week, probably more quantum next week. Discussion 109, this has been, and this is November 16th, holiday next week in the US. This has been for deep learning with quantum and classical parameters. Appreciate everybody coming on. Have a good rest of the night and have a productive rest of the week. Take care, everybody.